Yeah, so in last lecture, we ended up with the group 1 elements. Today, we will talk about the group 2 elements. Okay. You have your notebooks, or did you write this? Yes or no?
Yes,
Like
sir.
the last
Yes, sir.
lectures?
Yes.
Okay, you wrote it. Oh, okay, good, good. Okay. So we are learning about the group 2. So most of the things that we are going to learn about group 2 is going to be similar if you look at group 1. Acha, wait a second. Just wait 2 more minutes. Na? People are joining right now. Okay. Did we write anything about lithium and its anomalous properties? No, I think okay, fine. So let me start with the anomalous properties of lithium and the subsequent alkali metals, first of all. Okay. So lithium, it is the first element of group 1, first element of group 1, and its properties are quite different if I compare them with the subsequent elements of the group 1, subsequent elements of group 1. Why? The first reason is that lithium is very small. Lithium is very small. And the second reason is that lithium is 3 and it has one S2, 2S1. It has only S subshell. But if I go to the next element, that is sodium 11, it has 1S2, 2S2, 2P, 6, 3S1. So it also has P subshell, but lithium only has S subshells, and these are the two main regions. That is the size and the unavailability of P subshell, or the not unavailability, but there is no P subshell when you look at the lithium neutral. Now, first point is, since lithium is very small, since lithium is very small, its properties are different. Compared to other members. So the first property is it is hard. It is hard. If I compare this lithium to other elements, it is hard, and its melting point and boiling point is higher than other members. Is higher than other members. Next is lithium is least reactive. Lithium is least reactive because its ionization enthalpy is what? It is not. The ionization enthalpy is very high. So we can't remove the electron very easily because it is in the S subshell. But it is the strongest reducing agent. Least reactive, but it is the most, or I should say strongest reducing agent, and it is only because when we are going to react lithium or any other molecule with lithium, then we are going to do that in aqueous medium, that is in water. And in water, lithium has a very high hydration enthalpy. So if I put that lithium in water, then it can easily remove an electron. It can easily remove an electron. That is why it is the strongest reducing agent. Strongest reducing agent. Then if I talk about the oxides of lithium, then lithium is the only one which forms oxide. So lithium is the only one element that forms oxide. Other elements, sodium and all, sodium forms peroxide, the others they form superoxide. Okay, it forms superoxide. You can write a few more. You can write a few more things, but I think 4 is fine. You can write fifth one. You can write about lithium fluoride and lithium oxide. Yeah, lithium fluoride and lithium oxide are less soluble in water, compared to other members. Okay, compared to other members. So write this down. No, don't write this down. And then we will talk about now the group 2 elements. Okay, we'll talk about the group 2 elements. Now in group 2, what will be the general electronic configuration or the general outermost electronic configuration?
NS2.
NS2, very good. We have group 2 elements. Okay, these are known as alkaline earth metals. And what are the elements? And this radium is radioactive. General electronic configuration will be NS2, any noble gas, and after that you will have NS2. Valence electron, 2, oxidation state, plus 2, tendency to, they have tendency to lose electrons. All of these elements are what? They are metals. Right? They are metals. So we are done with the electronic configuration. Now we will look at things such as ionization enthalpy, hydration enthalpy. Okay. Important points are ionization enthalpy and hydration enthalpy. So first point, ionization enthalpy. So the trend is as usual, ionization enthalpy. So ionization enthalpy again, if I have an electron that is very far away from the nucleus, that means I can easily remove it. And hence, if I talk about starting with beryllium, right? Beryllium will have the highest ionization enthalpy, followed by magnesium, calcium, strontium, barium. We generally don't write the properties of radium because it is radioactive. Now, if I compare the ionization enthalpy, of alkaline earth metals to alkali metals, to the group 1. Okay, so the first ionization enthalpies of alkaline earth metal, they will be a bit higher than the corresponding group 1 elements. So what is the reason? Group 2 elements are smaller in size when compared to group 1. Hence, delta H ionization of group 2 is slightly higher than group 1. It is slightly higher than group 1. Next is hydration enthalpy. Hydration enthalpy. So you know hydration enthalpy. What will happen to hydration enthalpy? Hydration enthalpy, it will be directly proportional to the charge, because if you have more and more charge, that means more and more water molecule will be attracted and it will be interacting with the positive charge, and it will be inversely proportional to the size. Because if the size is high, the distance between the proton and the water molecules that is away, it will be becoming larger and larger. That is why you can say it is directly proportional to charge and inversely proportional to size. So if I talk about if I compare the delta H hydration, compare the delta H hydration of group 1, then group 1 has 1 charge, so it will be smaller than the delta H hydration of group 2. Since group 2 group 2 has what charge? Group 2 has +2 charge. Group 2 has +2 charge. And again, if I talk about the size of, or rather, let me start with hydration enthalpy. The order of hydration enthalpy will be beryllium 2 positive will have the highest because of its small size, followed by Mg2 positive, calcium 2 positive, strontium 2 positive, and barium 2 positive. This is the order of the hydration enthalpy. Now, let me talk about the size of hydrated ions. Now, since the hydration enthalpy is very high, its size will also be large, because more and more water molecules will be attracted towards Bg2 positive, followed by Mg2 positive, calcium 2 positive, strontium 2 positive, and barium 2 positive. Barium 2 positive. Okay, write this down. Okay. Now. Any doubt till here? Tell me. You guys have any doubt till here? No. Okay. No. Moving on. So these are the physical properties, and we can also write a few more things. Achha, those things you please you are going to read the chapter. Okay, please read the chapter. I'm going to tell you things which are more important and which I have to tell you the reasons of. Okay. Next is the chemical properties. Chemical properties. So first is reactivity towards air and water. Reaction towards air and water. Reaction with air and water. First thing is that beryllium and magnesium, they don't react with oxygen. Beryllium and magnesium don't react with O2 and H2O. With O2 and H2O. The main reason is that as soon as they start reacting, for example, this is beryllium, started reacting with oxygen or water, it forms an oxide. Even if it reacts with water or it reacts with oxygen, it forms an oxide, and oxide, it is like a film which covers the beryllium like this. Now, since all the beryllium of the surface, they reacted and they made a film like this. Now oxygen cannot, the beryllium is not going to get any oxygen now. Since it is not going to get any oxygen, no further reaction will happen. And hence, generally, we say that beryllium and magnesium, they don't react with H2O due to formation of an oxide film on the surface. Okay, an oxide film on the surface. Next we have.
Sir, so first they react with oxygen, then after that they don't react.
They react with oxygen, but they stop. Then like very small reactions. So that is why we say that it is like inert only. So that is the problem if we have the beryllium that is, I mean, it is when it is solid. Okay. So what we can do, if I want to react it now, then I can powder it. If I will powder it completely, so tiny bits, they are going to react. Yes or no?
Yes, sir.
Correct. So beryllium, if I want to react this with oxygen and I want the beryllium oxide, then I have to powder it, and then with some heat, because it is kind of a combustion reaction, with some heat, I will be reacting this with oxygen. Okay. So next point is powdered beryllium reacts with air with some heat, reacts with air with some heat to form. So it formed two compounds. First of all, it is obviously going to form beryllium oxide, and in air we also have nitrogen, so it also forms beryllium nitride. So one thing is that you guys figure out what will be the formula for beryllium nitride, है ना? आप लोग ये बताइए. Beryllium nitride. Figure out the formula. I will give you like 2 minutes.
Beryllium reacts with some heat to form the beryllium oxide and that beryllium nitrate.
Mamuna, you're saying something? Yes. Anyone? Beryllium nitride formula. Okay, see. Slight revision of your chapter 3. Whenever you want to write a formula, generally for ionic compounds, this is how you are going to write the formula. You have beryllium and you have nitrogen. What is the oxidation state of, sorry, what is the valency of beryllium? Tell me that. Forget oxidation state. What is the valency of beryllium? 2. What is the valency of nitrogen?
3.
3. Okay. Then you just do cross. B3N2. Got it, all of you?
Yes.
Okay. Now this is just what I would say. This is just a trick. This is how you also have to understand. Is there anyone who understood what is happening here? Think and tell me. Why does this trick works? ऐसे तो होता नहीं होगा ना nature में. You have to think about the formation of compounds, how in nature it forms. So in nature you should have neutral molecules, right? For example, NaCl, individually they have charges. Na is positively charged and Cl is negatively charged, but overall it is neutral. Overall it is neutral. If I look at beryllium and halides, so I will see beryllium and Cl2. That means beryllium has some charges, chlorine also has some charges. So in reality, you will be beryllium, there will be one chlorine, there will be one chlorine, right? So reality में ऐसे 2 नाम का कोई चीज तो होता नहीं है ना in maths. In maths we have 2, but in reality we have individual items like this. Okay, so the structure is something like this: BCl2, right? Now Cl is negative, and B is 2 positive. So we are what? Overall neutral. If I look here, Then I have Be, Be, Be. So overall charge here, it will be 3 into +2, that is +6. I have two nitrogens, nitrogen, nitrogen. Both of these nitrogens are -3, -3 into 2, it will be -6. Okay, so overall, again, these are neutral. So you have to get a combination such that even though the individual elements are in form of ions, but the overall molecule should be neutral. So this is Be3N2, beryllium nitride. Okay, so what about magnesium? Yeah, so magnesium also, if you heat a bit of magnesium, then it is going to give you magnesium oxide and magnesium nitride. Okay, similarly, Mg on heating, or rather ignition, I would say heating. What is the difference between heating and ignition?
So ignition means burning.
Okay, and heating means?
Supplying the heat.
Yeah, but if we are burning something, that doesn't that mean we are heating it? Hmm? Magnesium nitrate. Subsequent elements. Readily react with air. To form oxide and nitride. And they will react with, they also react with water to form hydroxides. Okay, so this is about the reactivity with air and water. Next is halogens. Reaction with air and water. Next is reaction with halogens. So in general, we will have a metal M. It will react with halogen, that is X2, Cl2, Cl2, F2, Br2, I2. And then what it is going to form? It is going to form MX2. And what is X? X is fluorine, chlorine, bromine, iodine. Okay, so it reacts with halogens to form halide. Group 2 elements. Halogens to form halide. Right, a star mark point. There is another way of producing BeCl2. Okay, nothing else, but only what? BeCl2. So we take beryllium oxide. And in the presence of carbon, I react this with Cl2 at some high temperature. So around 600 to 800 Kelvin temperature, you react this, and you are going to form BeCl2 plus carbon monoxide. So this is one of the most easiest way to get beryllium chloride. For beryllium chloride, there is one compound that is a complex compound. It has a formula which involves ammonia ion, that is NH4 twice, and BeF4. So if you just heat this a bit, you're going to get BeF2. Okay, so this is one of the methods of preparation of beryllium fluoride, and the above one is for beryllium chloride. Next is reaction with hydrogen. Reaction with hydrogen. Reaction with hydrogen. Now, in reaction with hydrogen, obviously, we are going to form what? We are going to form hydrides, right? Right, next. All group 2 elements form hydrides, okay, except beryllium. All others react with hydrogen to form hydrides. So how does beryllium form hydride? So right, BeH2 is formed by BeH2 is formed by treating VeCl2 with VeH2, VeCl2 with VeH2. So the reaction goes like this: VeCl2, sorry, with LiAlH4. BH2 to banana. My bad. Lithium aluminium hydride is going to give you 2BeH2 plus LiCl plus AlCl3. I think you will be using 2BeCl2s. So this is important. You can be directly asked. Beryllium does not react with hydrogen, but it still forms. Beryllium hydride. Yeah. So how does it form beryllium hydride? By the reaction with lithium aluminium hydride. Next is reactions with acid. So they are obviously going to react with acid and mainly the mineral acid that has protons. So you take any metal, you react this with HCl or something, you are going to get MCl2 plus H2 gas. So I'm reacting this with 2 moles of HCl. So they are forming what? They are forming chlorides. Here, that means in general, group 2 elements, they will be forming halides when I react them with some hydrogen halides. Fifth one, right? Fifth one will be the reducing nature. Reducing nature of group 2 elements. Now, if I talk about the reducing nature of group 2 elements, then obviously they are going to reduce things because they have a tendency to lose electrons. So they themselves have a tendency to get oxidized, and that is why they will be reducing others. So let us talk about the reducing nature. And always reducing nature, it is always happening in aqueous condition. So you have to look at two things: the ionization enthalpy and the ionization enthalpy, and also the hydration enthalpy. So we have looked at the ionization enthalpy, and I can say that all group 2 elements are good reducing agent. All group 2 elements are good reducing agent. But if I compare group 1 and group 2, then I can say group 2 elements have lower RP reducing power than group 1. Next, if I compare inside the group 2 elements, then obviously the Be2 positive, it is going to be beryllium. Our beryllium is going to be the best reducing agent, right? It's going to be the best reducing agent. Why is that? Why is it going to be the best reducing agent? Tell me, guys. because of high hydration enthalpy. Okay, you can ask, so you can write here Be2 positive is the Be2 positive has high ionization enthalpy, but still it is a good reducing agent. It is a good reducing agent. Why? It is a good reducing agent due to very high it is due to very high hydration enthalpy. Okay. Next is okay, let us write the order. So the most will be, we are comparing two things. The delta H ionization enthalpy, it should be low, and the hydration enthalpy should be high. Okay, enthalpy, ionization enthalpy should be low for a good reducing agent, and the hydration enthalpy should be high. So after comparison, you will obviously have to look at the data. Now the data suggests that the lower elements such as barium, radium, strontium, they are better reducing agent than the magnesium and beryllium. This is mostly due to the high ionization enthalpy. Okay, but it is still, there is a negative value. There is still a negative value. So the order is something like this: that you have barium, that is in the top. Barium is at the top, and it has comparable data. If I compare this to strontium, after strontium we have the calcium, and then there is beryllium. So this, in the group, this is the order. Beryllium, it should have had low, and it should have had, like, it should not be a good reducing agent because it is giving electrons by much difficulty because of very high ionization enthalpy. And if a good reducing agent is present, I need small ionization enthalpy. Okay, so the data suggests that this is the order for reducing character. Okay, next is the two structures: beryllium chloride in vapor phase and beryllium chloride in solid phase. So BeCl2. So in vapor phase, BeCl2, it exists as a dimer which has a structure like this: beryllium Cl. There will be another beryllium chloride atom here. Beryllium. So they are kind of bonded like this. Now in this beryllium, I can say overall beryllium has kind of 3 bonds. This is a partial bond. This is a partial bond, but beryllium, it has 3 bonds, and hence its hybridization is sp2 in this case. If I talk about the solid phase, this is known as a dimer. This is a dimer. 2 beryllium chloride is present. If I talk about solid phase, then beryllium chloride is something like this: BeCl2, BeCl2, BeCl2. So each beryllium atom, it is coordinating. So if I look at this beryllium, then I can see it has kind of 4 bonds, and that is why its hybridization here it is sp3. This is polymer. So in solid phase it is polymer, but if I talk about isolated BCl2 isolated, then it has chlorine bonded to beryllium bonded to chlorine. This is 180 degree, and it is hybridization is what? Sp. Hybridization is sp, but in solid it is sp3, and in vapor phase it is sp2. In vapor phase it is sp2. So this is all about the group 2 elements. Okay, this is all about the group 2 elements. I will talk a bit about the diagonal relationship between beryllium and aluminium, and also a few things that is different in beryllium if I compare beryllium to the other elements of group 1. Anomalous behavior. So first thing is that small size. Second is absence of d orbitals or d subshell. Since d subshell is not there, that means beryllium cannot show more than, it cannot have a covalency more than 4. It cannot have a covalency more than 4, but the remaining elements they can form till 6. They can form 6 bonds. Okay, if I look at the coordination compounds. Third is the oxides of beryllium is amphoteric. These are amphoteric. Okay. Okay, so this is all about the anomalous behavior, then the diagonal relationship between beryllium and aluminium. So these are the main points. Okay, these are the main points, and which will give you the reasons, for other differences also. So, but please read. Okay, read and go. Diagonal relationship with aluminium. The first relationship is that ionic radii of Be2 positive and aluminium 3 positive is almost similar. And that is the main reason for the diagonal relationship with aluminium. Second property that is very similar with both of them is that both aluminium and beryllium, if I look how they react with acids, so they don't get very easily attacked by the acid. Okay, and that is because due to a presence of the oxide film on the surface of the metal. They are kinetically inert. That means there is a possibility of reaction, but due to some hindrance, there is no reaction. They are kinetically inert due to presence of oxide film on their surface. Third is both forms compound such as, so beryllium, it forms a compound which has 4 hydroxy groups attached to it with 2 negative charge, and similarly aluminium also forms a compound which has 4 hydroxy groups and there is a negative charge. So this is one of the similarity. Fourth similarity is, as we have seen, that this type of bond is formed between beryllium and fluorine and beryllium. So it is a kind of what? It is a kind of bridge bonding, we say, because this chlorine is acting as a bridge between two beryllium atoms. So similar type of molecule and similar type of polymerization is seen if I look at aluminium also. Okay. Chlorides of both element have Cl negative bridged between bridged structure. I can also write chloride ion bridged structure. If this both are soluble in organic solvent, that means both of them have slightly covalent character. Both have slightly covalent character. Both have tendency to form complex compound, and most prominent complex compound of beryllium is BeF4 whole twice. Sorry, BeF4 2 negative, and AlF6 for aluminium. It is AlF6 3 negative. Okay, so these are the 6 properties which are similar in beryllium and aluminium. Okay, so that's it for group 2. Let me just give you the PDF, but please read. Okay,